Module 8. This is a built-in envelope audit. Now that we have covered how to measure and verify energy use, we need to look at the physical skin of the building, the wall, roof, and windows that enclose our conditioned space. Our goal today is to understand how thermal energy is transferred through this element and identify the key data points we must collect to improve a building's thermal performance. We have covered a significant amount of grounds leading up to this point. We began with the basics of energy auditing, moved through energy accounting and utility bill analysis to understand how a building's use of energy is charged. We then explore the financial side of economics, look at the tools typically used for energy audits, and most recently, the last one, we learn about the measurement and verification to ensure our project saving is properly estimated, calculated. Today we move from numbers to the building structure itself with this building envelope audit. We'll examine how the skin of the building, the wall, windows, roofs again, act as the primary barrier for heat and air movement. Our focus will be on understanding how heat transfer occurred through these elements and identify the data we need to such as insulation details, window types, to reduce the building's overall thermal load. For the most part, building envelope is the passive shell that separates our conditioned indoor air from the outdoor environment. An audit of the envelope is critical because it detects the load that every other system must meet. Our scope includes gathering data on building characteristics like its orientations, detailed window and door specifications, insulation status. Think of the envelope as a bucket. If the bucket has holes, it doesn't matter how efficient your pump is, right? You are losing water as the envelope losing energy. So using the energy first hierarchy here, in the professional audit, the envelope should be ideally addressed before mechanical retrofit, right? And reducing the building's heat loss allows us to downsize future boilers or chillers, right? Downsize equipment helps on saving significant capital cost. Here we define building envelope. In the simplest terms, the envelope consists of every element that encloses the conditioned space, the area we pay to heat and cool. Auditors, we must view the walls, roofs, and floors as thermal boundaries where energy is consistently trying to escape or enter. To audit this effectively, we categorize our data collection into three groups. Number one, building characteristics such as orientations, the basic construction details of the floor, the ceilings, fenestrations, they are openings like windows, doors, detailed windows and door information, as these are almost always the thermal holes in the skin, right? They are the weakest link in terms of the building envelope system. And then the insulation details. We must go beyond just the type and look at the actual status and the thickness to understand the true resistance to heat flow. Okay. Using the thermos analogy, a helpful way to explain this to a client is the thermos analogy, right? You can have the most efficient heating system in the world, but if the roof, the lid of the thermos is cracked or opened, or the glass, the window, right, is say single pane, the energy will dissipate very quickly. In Canada, where we face extreme temperature differentials, very big temperature difference, the integrity of this envelope often detects whether a mechanical system succeed or failed, right? The ASHRAE standard 90.1 provide a minimum energy efficiency requirement for the design and construction of building envelope. And you can also look at this real world case study here, Passive House. Look at Passive House. The standard, it relies so heavily on high performance envelope, extreme insulation and air tightness, okay, that many of these buildings don't even require traditional furnace, even in cold climate. Okay, sometimes a small resistant heating coil in HRV might work, or sometimes mini split heat pump would be enough. So yeah, look it up, Passive House. Okay. When we begin a physical audit, we start with the big picture, the macro view, okay, the big picture of the structure, the building characteristic. The first thing we should look is its orientation. Okay, in northern hemisphere, a building's long axis should ideally run east to west. That's ideal. This allows the building to maximize the southern sun exposure, like the solar heat gain, for free heating in the winter, while making it easier to shed the same windows in the summer. Okay, and we also look at the glazings, not only the building orientation, but also the glazing, the window orientation. Not all windows are equal. A massive glass wall facing west would be an energy disaster for cooling because it catch the low hot afternoon sunlight, where the south facing glass can be a benefit for heating. As an engineer, a designer, or auditors, right, you are not just counting windows, you are mapping where they face to understand why air conditioning might be struggling in some specific zones of the building. And finally, we look at the floor, the wall, and the ceiling details. This is where we identify the material of the assembly, right? In the wall, the thermal mass, like concrete, bricks that can hold a lot of heat, or light framed wood, steel that can react quickly to temperature change. Ceilings, since heat, the warm air will rises, right? And the ceiling's roof is usually the biggest area for energy loss. We need to know if it's a flat roof, a pitch roof, or a drop ceiling with unconditioned plenum above it. Floors is a slab on grade where heat is lost to earth, or is it over a ventilated crawl space, right? So the goal is, the key objective here is to define thermal boundaries, okay, the thermal boundaries. If you cannot tell exactly where the insulation starts and stops in these details, you cannot actually and accurately estimate the building's heat loss. Okay, thermal mass and insulation. So one concept is important here, right? Thermal mass, like concrete floor, versus insulation, like fiberglass. Okay. Um, Insulation slow down the rate of heat transfer. Thermal mass acts like a battery, right, that can store heat and release it later. So if you have a high thermal mass building, in that case, high thermal mass building cannot use aggressive night setback on the thermostat because it will take a long time, many hours to warm up that concrete back up in the morning, right? So lots to think about. Another real world case study here is the Lustron's homes. They use a lot of steels. So anyway, just Google it and you will see this kind of home, very famous in some way, not necessarily in the positive ways. Okay. And you should, when you see this, you should think about thermal bridging. Okay. All right. Fenestrations, windows, doors. So when we audit window and doors, collectively known as fenestrations, right, we are looking at the most complex part of the building envelope. Unlike the solid walls, windows must manage heat conductions, that would be thermal conductions, right? Solar radiation, and also air movement, air leakage, all simultaneously. First, let's look at the frame type. A metal frame without thermal break act as a thermal bridging. Okay, so we then also measure the window to wall ratios as well. Right, a building with say 80% of glass will have a very different energy profile than one with 20% window to wall ratio. Also, we must identify glazing and U values or its R value. Is it single pane, which is about R1, or U equal to 1 as well? Or double pane 0.5, that's R2, right? And or triple pane. So we have to look at the glazing itself. This tells us the thermal conduction rate, right? The thermal heat transfer rate. And we also check, is it open, or can it be, is it operable? Can it be open or not, right? Any misalignment. If there's any misalignment, then there can be infiltration as well. So these are some of the things that we have to check. Okay. Daylightings. Daylightings, if a building has many windows or skylight, can we turn the lights off during the day? Now, maybe we can save on lightings, but skylight might increase our solar heat gain and increase the cooling cost during the summertime. Right? Okay. Let me check. All right. One thing to mention here, if you go by a windows, there's another index that you might want to check, the visible light transmittance. We also look at the visible light. It's not shown on this slide here, right? This is the percentage of visible light, the light that our eye can see and sense, the percentage of visible light that can come through the window. A high performance window should have low U value and therefore high R value, and also high visible light transmittance. right? Allow us to harvest that daylight without the heat, right? We like the visible light, but all the invisible light, which is radiations, heat, we don't want those invisible ones. Okay. Once we move past the windows, we also need to look at what's inside the wall and and on top the window, right? Let's start with the insulation type, okay? Thickness and also locations. We don't just take the blueprint at face value, we verify it. Is it fiberglass bed, blown-in cellulose, or rigid foam insulations? Knowing the thickness allow us to calculate the nominal R values. Remember the thermal bridging guide, the exercise we did a little bit more than a year ago, right? And the different type of insulations. Also, if the insulation is damaged or if it's wet, the R value can drop to very low value, very low value if it's wet. So yeah, water is a very good conductor of heat, and so wet insulation actually steal a lot of energy from the buildings. Also, we look at if there's any gap. If there's any gap, then even a small 5 or 10% of insulation gap can reduce the effective R value of the wall by as much as 50%, right? Very small area. It's like thermal bridging again. Next, we look at the age and the condition of the roof. A roof near the end of its life cycle, it's probably a good, it's good for the energy conservation measured, right? A good project. If a client must replace the roof anyway, right? That's the perfect timing, the very low incremental cost time-wise to double the insulation thickness. Okay. Now, color of the roof. In our climate here, a dark color roof can help with the solar gain in the winter time, but in most of the commercial buildings, the cooling penalty in the summer is much higher. So use cool, the light color cool roof, right? It has higher reflectivity, can significantly reduce the building's cooling load by reflecting the solar radiation before it ever get absorbed and enter the insulation layer. Okay, look up the New York City cool roof. Right? There's a project they are painting on top of every or many buildings. They painted light color, you can see, and it has a reflective properties that can reflect sunlight. Very interesting. Look it up. Okay. And of course, thermal bridging. We talk about thermal bridging so many times, right? Now, building energy dynamics, right? In the summertime, our building acts as the heat collector because inside we have nice cool air temperature. Now we must account every ways energy enter the space or generated in the space, right? The internal heat gains. So the equation on this slide, very quite simple. You got thermal heat transfer Q1, even though it says it might say a conduction, but it's really the thermal conduction, thermal the convection and the thermal radiations, right? But in general, that's the thermal heat transfer. I like to use thermal heat transfer instead of conduction. And that's the heat migrating through the wall, roof, floor, windows, right? Due to temperature difference. Also, Q2 here, solar radiations. This is often the largest variable. It is the direct energy from the sun hitting the glazing area and absorbed by the roof. So part of it can be direct, and also through the solid, the envelope in general, the walls, it will slowly, and therefore it's a transient problem. Okay. And what else do we have? Number 3 there, infiltration, right? Infiltrations. This is represent the hot, humid, because it's summertime, so it's hot, humid air leaking into the conditioned space through cracks and doors or even windows if we keep it open. Also, internal heat gains. Number 4, this is the heat gain given off by people, equipment, and lightings, right? And lightings. Oh, actually, sorry. 4 and 5 both are internal heat gains. So this is the equipment and this is human here. We produce heat as well. So all the heat gains, it's all the terms sum up together. Now, look at the contrast in wintertime. The building is now a hot body, right? Our primary goal is to minimize heat loss during the winter time. So therefore, you can see now this is heat loss. So 1 and 3 is now heat loss. 1 again, thermal heat transfers because due to the temperature difference. Number 3, if inside we are leaking 20-degree air to outdoor, which could be 0 degree, -10, -20 air coming in to replace the 20-degree air, right? So that's also energy loss there. So 1 and 3 is loss. Now, the sun, it's actually heat gained. So for Q2, if it's heat loss, therefore heat gain would be negative. Equipment, lighting, and people, internal heat gains, so negative heat loss. All right. Can you see this infrared thermography? It's in the context of building envelope. This is one of your most powerful visual tools for providing invisible energy loss to a client, right? To a client. We use this infrared camera to see what our eye cannot see, right? Because it's a thermal radiation, right? It's thermal radiation. So the hot colors, the red and yellow, sometimes those are the heat loss. The bright color ones, right? Especially the red, you can see the relative temperature scale there. Okay. Group exercise. So think about this one and let's discuss this in the classroom, right? So think about what is the effect of the overall energy balance if we put skylight to the roof. So it's actually kind of given here. So think about it, and we can discuss this when we meet. Okay, heat transfer through building envelope, right? The building envelope is a dynamic boundary where energy is constantly moving in and out through conduction, convection, and radiation. Now, we break our analysis into different categories here, okay? Thermal heat transfer, which is sometimes called just conduction. This is the baseline movement caused by the temperature difference between indoor and outdoor environment, whether it's conduction through a solid brick wall or convection through the air pocket. The greater the temperature difference, the higher the heat transfer rate. Okay. Solar heat gain. This is one of the most critical factors for cooling load. It includes direct solar heat gain through glazing areas, which is transparent windows, which is why we document glazing orientations, right? And the transient part where the sun energy is absorbed first by the envelope and slowly radiate. Some of them going back to the environment, but some of it will go into the building. And also infiltration and exfiltration. This is the uncontrolled air movement. Okay, uncontrolled air movement. As we saw with the infrared camera, this is not just about draft, right? It's about conditioned air that we pay to heat or cool, escaping through cracks, and conditioned the unconditioned air forcing its way into the building. So as auditors, we don't just see a wall, we see a theory of thermal calculations. By quantifying these different categories, we can determine if the building's energy problems are due to poor insulation or high window to wall ratios, right, due to solar heat gain, or a leaky building envelope due to infiltrations.